Those pictures were taken using this telescope here at the Royal Greenwich Observatory. Now, professional astronomers use instruments this big to help them study planets and stars. This week, we're going to show you some of the astronomical things that you can do, including making your own telescope. And here to help us is Andrea Prestwich, who is an astronomer. Hi, Andrea. Listen, you don't need a big thing like this to see interesting stuff in the sky, do you?
No, there's lots of interesting things you can see with the naked eye.
So how do you go about doing all that?
Well, if you're going to stay up all night, you better wrap up warm.
Yeah.
It helps if you've got somewhere nice and comfortable to sit down.
Yeah, like a deck chair?
Like a deck chair. And most important, you need a star atlas.
Yeah, so if you're going to sit there all night, what would you expect to see?
Well, one of the most interesting things you'll see are shooting stars or meteors. And almost any night you can expect to see 3 or 4 of those. But at certain times of the year, particularly in August and January, then you can see meteor showers where you can see sort of 5 or 6 a minute sometimes.
Cool. And as well as shooting stars, how many normal stars would you expect to see?
Well, believe it or not, you can only see about 2,000 stars with the naked eye.
And you've got a way of counting them, I know, haven't you?
I have, if you've got the patience.
Oh, yes, here we go.
All you need is a frame, like an old coat hanger.
Like a coat hanger,
like
yeah.
a coat
Couldn't
hanger,
help noticing,
yeah. Which you line up with a couple of bright stars.
Yeah.
And then you mark in your atlas the area that you've outlined. I mean, I've drawn in a couple of squares here.
Yeah.
And then you count the number of stars that you can see.
Yes, while you're holding the frame.
While you're holding the frame, you count them you can see, you make a note of it, and then you move the frame to one side and count the next square.
And eventually you do the whole
And
sky in
eventually
sections.
you can
add
do
it
the whole
all
sky,
up.
yes.
Cool. So you reckon there's 2,000 there, but there's really millions and millions of stars up there. And I see you've got your binoculars hanging off here, Andrew. You reckon these are good to find a few stars?
Yeah, you can really see a lot more with a pair of binoculars.
Would you recommend that against, say, a telescope or something?
Well, a good pair of binoculars is much better than a cheap telescope, yes. I mean, with something like this, you'll get really spectacular views of the moon, and you'll be able to see some planets as well.
Oh, tremendous. Talking of planets, this thing's a planisphere, I see. Explain to us what that does, then.
Well, this will show you what stars are visible at different times of the year.
Yeah.
So all you have to do is to match up the date and time along the edge here, and it'll show you exactly what stars are visible overhead.
Yeah, there's a sort of window there, and they're all displayed in the window. Yeah, great.
That's right, yeah.
But it doesn't show you the planets, apparently.
No, it doesn't. It's called a planisphere. But in fact, it doesn't show you the position of the planets at all. It just shows you the position of the stars.
Angela, thanks very much indeed. Look, if you haven't got a pair of binoculars, but you'd like to use a telescope, you can make your very own do-it-yourself reflecting telescope, like this. Look at that. It's called a Dobsonian and has been designed especially for us by the Junior Astronomical Society. All it is a length of plastic drain pipe with a 9-centimetre curved mirror at the bottom and a little flat mirror at the top. Now, it works very much like this big telescope, except that the mirror in the big one's about 10 times the size of this little one. See, light goes in at the top, bounces off the bottom mirror, and it comes back up to this little one, then out of the side through this eyepiece. And you can focus it by moving the eyepiece up and down, like that. Now, the tube is mounted so it can tilt up and down and swivel. That's, of course, to compensate for the movement of the Earth, which makes the stars look as if they're moving across the sky. Of course, we're moving, they're not. Now, it has a curve on it, rather like the one on a shaving or makeup mirror, like this. Okay, this is the flat side. And this is what the curved side does. Now, if you've got one in your bathroom, you want to try holding a piece of paper about 2 feet away from it and focusing an image of the bathroom light onto it with the mirror. I'm going to do it with this mirror and try and see if I can get the image onto the stand we've got for the telescope. Where's your light one? There we go. Yeah, there you go, see? Ah, it works. Brill. That's the filament in the light. It's being focused by the mirror. Now, you may ask, why bother with a huge telescope when you can use this one? Well, the bigger the mirror, the more you can see. Look at these. This one is through a big telescope, and this one through a small one. Now, they're both of the same thing, but you can see much more detail in this one. Technically, it means it has a higher resolution. The other thing is that a large telescope collects more light and can enable the astronomers to see very dim things like these. One other interesting thing to do on a clear night. Now get hold of a camera. Any camera will do with a standard lens. In this case it's 50mm, but there must be a way to keep its shutter open for a long time. Now this one has a locking cable release on it, and if you didn't know what this was, like I didn't, I will now show you. If I push that down, that click opens the shutter. I'll hold it down, fix this little thing on here, that will hold it. Then when I release it, the shutter closes again. Okay, now put it on a tripod pointing north and tilt the camera towards the sky. About that sort of angle is about right. Now put in a high-speed colour film, prints or transparencies, 400 ASA will do you, and open the shutter for 2 or 3 hours. Now when you get the pictures back from the chemist, this is the sort of thing you'll see. Try changing the exposure times. Try 1 hour, 2 hours, 3 or 4. Try all night if you can and see what effect this has. By the way, this works best away from the city, as the street lights tend to spoil the pictures.
Well, we're doing a programme about astronomy, so it may seem odd standing out here in the broad daylight, but it's often quite difficult arranging to look at the stars at night. So, to see what we can do during the daytime, I've got another astronomer here with me, Nigel Henbest. Hello, Nigel.
Hi.
What can you do by way of astronomy in the daytime?
You can do something during the daytime that the professional astronomers can't do at night, even with their big telescopes, and that's to look at a star in close-up, because the sun up in the sky is actually a star, the same as the stars at night, but the ones we see at night are so far away that even with a big telescope we can't see very much. The sun is so close to us that we can actually see details on it, using even a very small telescope like this one here. This is a small refracting telescope with a lens at the top which concentrates the sun's light down to the eyepiece and forms an image of the sun just down there.
Well, of course, typical British weather, we can't see the sun today, but even if you could see the sun, I would think it very dangerous to point a telescope at it and look at it.
Absolutely, yes. Please never use a telescope to look at the sun directly, and not even binoculars, because both of them will concentrate the sun's heat as well as the sun's light there. So when you put your eye there, you can blind yourself, so never do that. But you can look at the sun safely by projecting the image from the eyepiece onto a screen that we have over here. Twiddle the focus knob to get a sharp image of the sun. We won't see it today, of course, because it's cloudy. And you have another screen up here to stop the sunlight falling directly onto your image down here.
Now, is that a drawing of what you saw yesterday?
That's right. It was clear yesterday, and we had a lovely view of the sun. It projected size in the image, and there are a couple of dark spots there, we call sunspots. And to give you an idea of how big the sun is, each of those spots is about the same size as the Earth.
And are they there every time?
Not all the time. We don't see the same sunspots. Sometimes you'll see some, sometimes you won't. And one of the interesting things to do is to keep looking at the sun day after day and see what happens to the spots. I have a book here of drawings done over successive days, and here, for example, there's a big group of sunspots up here. If we look the next day, you'll see they've moved a bit to the left, and the next day they've moved even further to the left.
So they're floating across the surface, are they, of the sun?
They're not actually floating, they're fixed on the sun's surface. It's just that the sun is spinning around, just as the Earth turns around once every 24 hours. So the sun turns around about once a month.
And so in a couple of weeks' time, they'll come around the back?
Yes, if you wait long enough, the big ones will come around to this side again, and you'll see them reappear. If you look longer than that, you'll see that the number of spots on the sun is never the same. This year, for example, there aren't very many spots on the sun. We call it a sunspot minimum. But in a few years' time, you'll see a whole lot of spots, and they come and go in a cycle of about 11 years.
Well, all of this, though, is a bit expensive, isn't it? This telescope must cost a few pennies, so is there anything you can do that's a bit cheaper?
Yes, there's something you can do for nothing at all, and that is to see how the height of the sun varies in the sky. Now, the sun's at its highest point at midday each day, but that's not always the same. If you're looking at the height of the sun, don't look at the sun directly. Again, it's dangerous. Even with your naked eye, you can damage it by looking at the sun.
Yeah.
But what you can use is a stick. Any stick will do. Here we have one here. Just stick it into the ground and look at the length of the shadow. Because when the sun is high in the sky, the shadow is going to be short, and when the sun is lower, the shadow will be longer.
And you keep a record of the length of the shadow then all the year round?
Yes, do that every day and see what happens during the course of the year.
Well, thank you very much, Nigel. So, go with the shadow stick experiment when there's some sun around and try and work out why the sun seems to change position in the sky. Could this explain why summer is hotter than winter?
Astronomers use the light coming from the stars to help them work out what they're made from and what different chemicals there are inside them. Now, you've probably seen this before. It's a prism making a spectrum. The white light is spread out or dispersed by this prism to such an extent that you can see all the colours that are usually mixed up together. Now, the white light coming from the sun is very much like this light, but remember, the sun is making light by actually burning the stuff it's made from. If it were burning different chemicals, the arrangement of the spectrum would be different. For instance, here we've got a sodium lamp, and you can see that the light is predominantly yellow, and in fact, if you put a prism in front of it, you'd get a very different looking spectrum. So you can think the spectrum is a bit like a fingerprint. So what the astronomers do, they stick an instrument called a spectrometer on the end of their telescope and make spectra of the light coming from the stars, like this. This is a spectrometer plate. If I can hold it so you can see it, there we go. In fact, it's a black and white photograph of the spectrum from a star. And these little tiny black lines here show the position of the different colours in the spectra. And from this, they can tell what chemicals are being burnt to produce the light. It's fascinating. Right, the telescope spectrometers cost thousands of pounds, but you can make a cheap spectroscope, one like this. Only cost you a few quid. Now, instead of a prism, which is a bit bulky, it uses a plastic material called a diffraction grating. This is a sheet of diffraction grating, and if you hold it up in front of the camera, like that, you can see there are colour fringes all around the edges. Now, the colour fringes are the beginnings of a spectrum. Look, I'll just put it half like that, and you can compare with and without the diffraction grating. There, like that. Now, if the angle is right, we can get a good spectrum. OK, we're going to use a tiny bit of diffraction grating that has already been mounted at the right angle. See, a little bit perched on there. All we have to do is to make a paper tube to fit around it like this. And there's a bit of paper over the end with a slit in it, and at the other end there's an eyepiece. OK? Now, you can see the sun spectrum if you look at sunlight, but don't look directly at the sun, but at a piece of white paper, or better still, at a clump of clouds. Now, you get interesting spectra if you look at fluorescent tubes and street lamps, and you can even start to look at the light from different chemicals. Right, now, using a bit of silica rod, I'm going to dip it into some different chemicals and into the flame. Just put my goggles on in case they're going to spit at me. Right, I'll just put a bit of water on the rod. It just makes you stick to the rod a bit better. This one's copper sulfate. The copper's the important part, that's what we're looking for. There we go. Let me just hold a bit in the flame. Hey, look at that. Now, that green colour is a characteristic colour of copper. But more important, look at it through your spectroscope, and you'll see the spectrum, the different spectrum that copper creates with its flame. I'll have a go with another one here. I think, yeah, we'll pick this one. This one's got strontium in it. Let's see if I get some bits to stick on. Get on. There's a little bit there, that might work. Please, let's see what it does. Oh, yes, look at that, smashing. A bit more? No. But that red flame is the red strontium flame, and again, look at it through your spectroscope and see the strontium characteristic spectrum. Now, you want to try a whole range of chemicals and see what they all do. Different spectrums for all of them you'll find. But when you are looking at a spectrum in your spectroscope, you may see some black lines mixed in with the colours. What do you think they are?
So far, we've been looking out into space. But did you know that out there are plenty of things looking back at us? In fact, Britain has its own space probe called UOSat-2, which was built by amateur radio enthusiasts. And as it orbits the Earth, it sends back information on the 60 experiments it has on board. You can pick up those radio signals using quite cheap equipment like this, and a micro. And this is the sort of thing you get. A complete printout of all the experiments. But of course, Eurosat is only one of a whole range of satellites that you could receive. Take a look at this. A modified television aerial, a weather satellite receiver, a bit like an FM radio, and a microcomputer, all you need to capture pictures of the Earth from space.
You see a picture building up. One side you've got it invisible, infrared, and the other side you've got the visible light.
This was taken by an American satellite called NOAA 9 as it passed overhead. The picture is sent at 2 lines a second, and the computer gradually builds it up on the screen. And although they aren't quite up to the standard of those seen on the weather forecast, you can make out Italy and Sicily. But because of the way the satellite works, they're a bit stretched out.
What we've got to do is work out when we can acquire the signal from NOAA 9. So what I'd like you to do now is to use the orbital prediction program to find out when we can actually receive the signals. Okay?
The computer is a great help. Just type in the time and the date, and it plots the satellite's ground track. This is the path it traces over the Earth's surface. NOAA 9 passes over the North and the South Poles.
You should find it quite difficult at the top though, because you're matching the projections.
It's longer as well.
It's difficult to see on the map, but if you trace the path on a globe like this, you can see that each time it comes round, it's over a different part of the Earth.
So it comes down.
So everyone around the Earth gets a chance to see a picture during the day, but only once or twice. For more regular pictures, a dish aerial picks up signals from Meteosat 2, 34,000 kilometres away.
Tiny tip of Africa by here.
What's this bit here then? It's France, isn't it?
For those without computers, digital frame stores can produce some staggering results.
Cornwall down there. This bit's cloudy, right?
Meteosat 2 orbits at the same the Earth is rotating, and so it seems to stay in one place.
Yeah, there is a bit of space.
It sends a continuous stream of pictures that show the weather as it actually happens, and you can even check out the maps as well.
Oh yeah, Morocco.
Morocco.
Yeah.
Meteosat 2 takes a picture of the whole Earth like this. There you can see the bulge of Africa, and down here is South America, but it also transmits in sections. There, like this, to give extra information. But have a look at this picture. It's the one that came in yesterday afternoon, about 3:30, from NOAA 9, the polar orbiter. The one you can see there is the ordinary light picture, and there is the infrared one. Now, by combining the two, you get a bit extra information, but a bit difficult to see in black and white. So have a look at it in colour, and you get the three-dimensional effect showing the cloud height and the thickness. And with a bit of skill, you should be able to tell which one is rain. Let's see, where are we? There. Pretty miserable as usual.